we've seen the Heisenberg uncertainty relation. Heisenberg uncertainty relation, you've done a lot of calculations with. We used the standard deviation in x times the standard deviation in momentum was greater than or equal to a minimum amount of h bar over 2. Now, do you recall what I said was the origin for Heisenberg with this?
I don't recall the origin, but I recall the joke behind it.
Well, I mean, that is kind of important. It was from using a Gaussian distribution. So you have a wave packet that's a Gaussian distribution that gives you a wave packet and frequencies, and taking the uncertainty you have in the wave packet and frequencies, that's the standard deviation, and the uncertainty in the position from the position space. He's able to show that that gave you the minimum possible combination of the uncertainties. So that's how we had the Heisenberg uncertainty relation. Now we're going to look at this as a generalized principle rather than that specific case. So this is basically following directly from your textbook. I hate to follow too close to the textbook, but at the same time, I hate to go away from the textbook because, after class, what are you going to refer to? What was he talking about? And for something like this, I think it's important to follow close to the textbook and to make sure you understand what the pieces are. So we're going to be going through some, I consider them a little hairy derivations here to find what turns out to be a fairly simple and fun result. Fun, okay. I'm a physicist when I call it a fun result. Sure. So the uncertainty we had seen before was the square root of the expectation value squared. Whoops. No, I was right. That's what we have been working on all semester. And so that's what this first statement is. Now notice it's just squared on both sides. So it's the same equation. And then it's expanded out to using the bracket, the Dirac notation. I actually always prefer to write it like this, but I think that's the way the textbook did, so I wrote it consistent with the textbook. It's 6 of one, half dozen of the other. And then we're going to go to something a little different. We're going to define a new vector. Now, we've been talking about completeness and Dirichlet's theorem. We had that on the test. I did the solution for the test. I know. I don't have a grade for it yet. And given that I only have one free hour all day today, it's unlikely I'm going to get a grade today. I will. And the homework, actually, you'll be reminded of what you answered on the test, will help you with a couple of homework problems. And what we're doing today will definitely help you with a couple of homework problems. So we need to get through that, but I want to get the test grade back to you. I didn't even post the solution last night. I figured it was too late at night. My brain doesn't work that well at night, and so I'd wait and review it before I posted it. So, but using that idea of superposition, we have a complete space. We can always take a steady state solution, or a wave function, and put it in terms of a linear combination of steady state solutions. And here we're taking something that's kind of like that, but a little different. We're just going to say, let's define a new wave function that is this operator minus the expectation value of that operator times a steady state solution. And of course, at first glance, it seems kind of dumb. Like, why do you want to do that? And the answer comes in, we're going to close that on itself. So we're going to do remember, if it's the bra, that means that it's actually the complex conjugate when we get to integrals. So if we were going to show this as an integral, well, first I'll show it without the integral, and then I'll show it with the integral. That's just the simple expansion, and showing it as an integral would be the integral over all space. I'll put the dx here at the beginning so I don't forget it at the end. I should have been consistent in my color coordination. So that's what is meant by, the bra F ket F. You can see why we like the Dirac notation, because it's a lot shorter to write without having to put the integral sign, without having to put the stars for complex conjugate. Also, keep in mind that expectation values are real. So this equals that. So we're going to stay in the Dirac notation here for the rest of it and not show out the integrals. And so, of course, I already wrote this, and then we expand. So you expand, you're going to have the first term in the bra, the first term in the ket. So this is the first and the first. And then we're going to do the second in the bra with the first in the ket. Then the first in the bra and the second with the ket. And finally, the second in the bra, the second in the ket. So the first in the bra, of course, is the numbers. So when we do all of that, notice there's no stars on either of the expectation values because it's the same value, it's real. And so we take those. What does this here give me? That's expectation value of A. What about this here? It's also the expectation value of A. And so all three of these terms are the same thing, 2 negative, 1 positive. So the easiest way to do this is, let's say that these add up to 0. And then I just have those first two terms. And so that's equal to, this here is going to be the expectation value of A squared, because just to make sure we're clear, the way that the Hermitian operators work, that equation is true, which is also one of your homework problems is using that. And so since I had an A there and an A there, just make that an A squared. Hence the expectation value of A squared. So bra F ket F is equal to the uncertainty in A squared. That's why we introduced it. Well, it's half of why we introduced it. Now we're going to likewise invent a B vector or G vector that's based on the B operator, and it'll have the same relationship. And then we use the Schwarz inequality. The Schwarz inequality is shown in our textbook. It's not derived in our textbook. You have footnote 5 on the page, footnote 5 on page 77? I got to look. That says, hey, if you want to see a derivation, go here. Nope, it's not page 77, that's for sure. And it's not page 97 either. Where was it? Page 95. Footnote 5 on page 95. For proof, see Rish and Naji, blah, blah, blah. But the Schwarz inequality, since you've got the book out there, if you look there, it's equation 3.7, says that for any random functions f and g, that the absolute value of the integral of f star g is always going to be less than or equal to the square integrals of f mod squared times g mod squared. That's square integral of f mod squared times the square integral of g mod squared. That's the Schwarz inequality. And so our uncertainty relation, well, taking the product of the standard deviation in A times standard deviation in B squared is equal to the F bracket G. And by the Schwarz inequality, that should be, notice this is greater than or equal because it's flipped the order of what's shown in equation 3.7. The magnitude of bra F ket G mod squared. Well, yeah, I said magnitude and then I said mod squared. Magnitude didn't need to be said there. So just applying that Schwarz inequality, we now have what seems like a non sequitur. When I was going through this, I was like, wait, do I have something out of order? I had to look back in the textbook to make sure I didn't have things out of order. The magnitude of Z is, by definition, well, minus, it's not minus. Yeah, it is minus I squared times the imaginary part of Z squared. That's being real technical. But of course, minus I squared is plus. And so that's why there's a plus there. And so if Z is complex, you're always going to have the magnitude of Z mod, well, once again, you don't need to say magnitude. Z mod squared is always going to be greater than or equal to the imaginary part squared. It will also, conveniently enough, be greater than or equal to the real part mod squared. But here we're focusing on that imaginary part squared and realizing that the imaginary part squared is Z minus Z star. Z minus Z star, the real parts stay the same, so those are subtracted out. And then you have an imaginary for both of those terms. So when you square it, you're going to have I squared. The 2 here is because this is going to be 2 times the imaginary part. The I is because it's going to be imaginary, so you are subtracting out dividing out the imaginary. Why do we do all that? Why, you ask? Well, why, I ask again. It's because we are going to look at this magnitude of Z mod squared and use that substitution. This comes from that, right? The 1 over 2I and then Z minus Z star. FG is the complex conjugate of GF. And so we're saying now that we're always going to have this product is greater than or equal to what I have in the box. Life is good. Doing these derivations just seems to drag on and on. And, I talk, and if you miss one step, you miss the whole thing. So I hope that we're following along. Now we're going to actually calculate what this is. Of course, this is in general calculation. We don't have a specific what A operator is or what B operator is or what psi is. But using the bracket notation, we once again have, I'll use different colors this time. I'll be smarter. And I'll call it 1, 2, 3, and 4. So this is but apparently I won't color coordinate like I thought I was. So this is going to be 1, Come on. Okay, so there's once again the combinations of expanding that. And just as before, we look at this and we say, this is expectation value of B. This is expectation value of A. This is, what's that?
One.
One, yeah. So, so we had expectation value of A, expectation value of B, expectation value of B, expectation value of A, and expectation value of A, expectation value of B. So once again, all those three are the same. Just like before, it's going to end up with just one of those negative because two are negative, one are positive. And then this here, once again, using the definition that it's a pretty straightforward identification. So we have FG is equal to expectation value of AB minus expectation value of A, expectation value of B. And then separate calculation, if we reverse the order, the only difference that's going to make in all of this work is reversing the order of these two. So up here we had the difference in bra F ket G and bra G ket F. So we have bra F ket G, bra G ket F. We take the difference and these two terms here subtract out when we do the difference. Those are apparently the real part. And these parts leave expectation value of AB minus expectation value of BA, which we can combine to be the expectation value of the commutator of AB. At this point, I tend to think of, I don't know if you guys have ever seen the TV or the movie Better Off Dead. Have you seen it? No. It has a teacher who's teaching, I think it's biology, and it's really dull, and he's going through, and the students are just rapt attention, and they're all clapping, and it's so exciting to them. That's how I feel here. Except for I'm feeling like it's never going to be that way. Everybody's going to be bored because it's not really exciting, but I feel like I've really gotten somewhere here. I now have, if I look back at the beginning, and I'm sure I have at the beginning of the next slide, but I'm going to write it here because it's so exciting. So this greater than or equal to 1 over 2i expectation value of commutator of A, B. Yeah. Yeah.
Is that entire right side squared?
Did I miss something? Yes, it is. Darn it. So much for my excitement. Well, here it is rewritten correctly in case I made a mistake, such as that. Yes. Well, yes, I could have erased the squares on the other side and said, yes, I meant to do that. I meant it that way. All right. So there's our uncertainty relation. We're done. I know. Almost seems anticlimactic after I made a mistake in the last line, but you know, what we have is a generalized now uncertainty relationship between any two variables. So now we can take something like, let's say two variables commute. On the test, you saw, for instance, that, well, you hopefully saw that the potential energy and X commute. So if I'm trying to measure the X value and the potential energy value, the commutator is 0. My uncertainty relation is 0. There, I can get both of them exactly at the same time. So if things commute, you can simultaneously know their expectation or know their values. If they don't commute, there's always going to be an uncertainty relation. And so now we can calculate the uncertainty relation between any two variables. Of course, the one that we started with was between momentum and position. And so I can just test Heisenberg uncertainty relation against our now generalized. So the commutator between P operator, well, let's be consistent. Do you remember that commutator?
Is it IH bar or IA?
It's H bar. Now here's the tricky part. Is it positive IH bar or negative IH bar? I think it's positive too, but because I'm the teacher, I have to know. So I'm just looking in the textbook because I don't feel like actually doing the commutator calculation again.
At the very front, it's third one from the bottom on the left.
The very front of the textbook? Oh yeah, there it is. Okay. So XP is positive, so PX is negative then. And that's why we check. So that would give us the uncertainty between momentum and X is greater than or equal to 1 over 2I times I minus IH bar Now you look at that and you're a little bit wah wah, right? Why you're a little bit wah wah? Because I have a negative. But you know what? Does that make you feel better?
Yes.
Because my uncertainties are always positive values. I can't have a negative uncertainty. And so I'll put that absolute value sign there. Because what's the difference in sigma p, sigma s, and sigma x, sigma p? There's no difference. They're both positive values. The order doesn't matter. So it has to have the absolute value sign there. And that makes h bar over 2. So our generalized uncertainty relation certainly agrees with the Heisenberg uncertainty relation. It does not say, ooh, Heisenberg underestimated or Heisenberg overestimated. It said Heisenberg hit it. Is that the only uncertainty relation possible? No. Any two variables. What's another set of variables that we commonly look at?
The Hamiltonian, probably.
Well, we commonly look at the uncertainty between energy and time. And to put the answer before the problem, it turns out you have the same uncertainty relationship. It turns out that your uncertainty in energy multiplied by your uncertainty in time is greater than or equal to h bar over 2. And based on that, you would think, well, it's always h bar over 2, right? And you would be wrong. In that case, it's the same h bar over 2. So we're going to look at, oh, look, hey, I have the commutator right there if I would have gone to the next slide. I should just go to the next slide and not try to think as I lecture. Thinking's bad. You make mistakes when you think. So looking at energy-time uncertainty relation. What am I doing here? First things first. Time. If I want an energy-time relation, I have to look at how my values change in time. And so I have here, I'm going to calculate the rate at which the expectation value changes. So this is just definition right here. And this, well, this is definition right there. What am I doing for this part? Expanding, I'll take that. It's the product rule. My son's taking Calc 1 right now, so he's going to have a test on Wednesday where he'd better know his product rule. So we're just using the product rule, taking the partial derivative of each part there. And so now I have an equation for the time variation in an expectation value. We're not leaving that. We're now saying, whoa, we have this here is something from the Schrodinger equation that will relate this and this. So we're going to use the Schrodinger equation to find what the partial derivative of our wave function with respect to time is. So of course all you have to do is divide both sides by that IH, and you have the partial derivative with respect to time is minus I over H bar Hamiltonian, I know that's where you went, Chris, or Indy, times psi. So I can substitute that in, so I can say and I'm sure this is the next line on the next slide, but I'm still going with that thinking part. Well, the first one and the last one are going to be factor out the minus I over H bar for both of them. So keep in mind, I said the first and the last. I'm changing the order. Oh, mistake. Where's the mistake, you ask? Yep. Because it's complex conjugate when you move it out, so you've got to change the sign there. So now I got to think about which one's going to be, this one here is the one. Well, let's get rid of that minus sign, change this to a minus sign. And that should be what I have right there. And yeah, see, sign corrected. Once again, maybe I just shouldn't try to think. So we get to this equation, and this is the full solution. Huzzah, yay, yippee, skip. Well, we never put that there. There is the equation for the time derivative of the expectation value of some random operator. In almost all cases, our operators are time independent. If it's time independent, what is this going to be? Yes. If Q independent of T, and so we're going to have our time variation is I over H bar times the expectation value of the commutator of the Hamiltonian with whatever my operator is. So now I have something that talks about the time variation, and I can start talking about the uncertainty relationship between time and energy. So Y and energy, well, we had the Hamiltonian there. And so finding the the commutator between the Hamiltonian and some arbitrary operator is shown as reversed there, so that we can use our uncertainty relation. So our uncertainty between the Hamiltonian and my operator Q is shown here with this calculation for the time variation in the expectation, or in the expectation value. So just going through what's going on this page. This right here is exactly this right here. And of course, I should have included the minus IH. So this stuff with the, what color would we call that? Pukey Bronco color? Something like that? Orange? That's the expectation value of the commutator between H and Q. And then we had all the rest of this was from our derivation of the uncertainty relation between H and Q. And so because of this square, I had the i's cancel. H bar over 2 squared was H bar squared over 4. Then I square rooted to get back to H bar over 2. And let's see, this here, the expectation value, this here we said is almost always 0. And now we're ready to actually apply this. But still there's a tricky part. How do I determine the uncertainty in time? This here was the uncertainty in the Hamiltonian, i.e. the uncertainty in energy, and the uncertainty in some operator Q. And so what we do is we say the uncertainty in time is the expectation, or is the uncertainty in Q divided by this derivative of the expectation value of Q with respect to time. Then we put it in. That gives us our relationship that if we take this to solve for sigma Q, this one here, I'm not absolutely sure I'm doing right. So my uncertainty in time is this, my uncertainty in energy is that. So if we multiply them, keep in mind this was a greater than or equal, so I actually have a greater than or equal there. Yes? So there's the uncertainty in energy. And so we have greater than or equal to H bar over 2. And then I have this term here. Oh, wait. I forgot to divide there. Well, I made a mistake. If I divide there, it's going to divide that out. And so that doesn't appear there. And we get the right answer. Totally forgot that. So this uncertainty in time, the calculation for the uncertainty in time is the part that's a little tricky on that. But we get the same uncertainty relationship, it turns out, between energy and time. Now, why is that important? You guys are obviously very familiar with Blake. And Blake, his research area is in high energy physics, right? Now, I haven't talked to him about this, but what I know about high energy physics is that they use this relationship to infer things. So this is kind of working it backward of what they really do. This comes from our textbook. It says a delta particle lasts about 10 to the minus 23 seconds. You know what no human can do? Yeah, time anything that fast. So that's why I said we're doing this backward. There's no way they measured that time as 10 to the minus 23 seconds. Instead, they do what we're going to do here to infer that time. So if you make a histogram of all the measurements of its mass, you find you have a bell-shaped curve centered at 1232 MeV per c squared, which reminds me I should have put MeV there, with a width of about 120 MeV per c squared. If you look in your textbook, which you now both have out, so figure 3.2, it shows a graph of that histogram. So that's the bottom of page 117. Now I'm going to draw my own variation of this, just so you can laugh if you need to. So here is remember it's a histogram, so frequency means how many times per delta E. And then you have the rest mass. You have something that goes like this. So this is the kind of data they actually get. Now, there's lots of different measurements they make in high energy physics, but this is one of the very common ones you see. So they get this information, and you take this and you say, well, the average there is probably the actual mass of that particle I'm measuring. And so if that's the mass, what can I infer from the uncertainty? And we take that and we say, well, that is actually going to have to do with the uncertainty relation here. If we have a certain uncertainty in the energy, there's going to be an uncertainty in the time that we make that. And so from the of course, to get the energy, you take the rest mass multiplied by c squared. And so that's just 120 MeV. Then you say, well, delta energy times delta time must be greater than or equal to h bar over 2. Therefore, delta time must be greater than or equal to h bar over 2 delta E. That's what they actually do to infer that 10 to the minus 23 seconds. So let's just check this. H bar over 2 is, well, H bar is about 10 to the minus 34. Right, between friends, I can round it off.
Yeah.
Yeah. So I got that. Then I need to do a conversion between joules and MeVs. So I have my brain is shot. It's 1.602, right? Well, it would be 19. It's 13 to go to MeV.
Oh, right, yeah.
And that's not how you write 13 in any system. So that can't be the right conversion. Yeah, that ain't the right conversion. It's kind of right, except for it's inverted. 1 joule is 10 to the minus 13. That would be the right conversion, right? Because 1 MeV is a small. So now we cancel those, and we'd have, well, unfortunately, that's about 5. I'm like, between friends, which way do we round 5? So let's just do it as it lies. Yeah, you guys have calculators. I don't.
Well, I got 2.7 times 10 to the negative 24.
Yeah, like I said, it was close to 5. I don't know which way to jump on a 5. Right, if it was 2.5, it would have been right at 5. So, or 2.5? No, if it was 2, it would have been right 5. Anyway, forget it. So this is actually the uncertainty estimate for time. Delta T is greater than or equal to 2.7 times 10 to the minus 24 seconds. And so what they say is there is absolutely no problem with this uncertainty in the energy, because as long as I can have violations of conservation of energy. And you hear that and you're like, I've been in physics a long time, and they pretty much said that's a fundamental rule. We have a name for it. It's the first law of thermodynamics, right? Energy cannot be created or destroyed. And yet here we have an uncertainty relationship between energy. And so the way we interpret this is, I can totally have energy conservation broken as long as it's broken for a time that's smaller than that specified by this uncertainty relation. I can break it as long as the energy violation times the time in which that violation occurs is smaller than h bar over 2. Then we don't have a problem with it. And that thinking leads to the only plausible explanation for how the Big Bang could have occurred that doesn't require a God. And that is a quantum fluctuation. Have you guys ever heard of the Casimir effect? No, but it sounds interesting. It's not something we're going to talk about in this class because we're pretty fundamental quantum physics. But you can have a perfect vacuum. And in that perfect vacuum, you will suddenly have appear a particle and an antiparticle. That would be a violation of conservation of energy, right? Because you suddenly created particles with mass, with energy, where there was nothing. And so in a perfect vacuum, you actually don't maintain the perfect vacuum because of this Casimir effect. And so they talk about, like I think a Casimir pressure or something. It's not something I'm well versed in. How can that occur? The uncertainty principle allows for it to occur. But of course, keep in mind that the delta T gets smaller for the bigger delta E. And so the particles you're created here are really low mass particles, so it's not as big of a violation. That idea is then extrapolated to say that we could have the entire universe have formed in a similar reaction. Except for, do we ever see electrons and positrons spontaneously appear? No, we see photons that will decay into an electron, a positron, but that's energy converted into energy. We don't see electrons and positrons because higher energy makes it lower probability of occurring. And yet the only answer, at least as far as I know, for scientists for how the universe could have started is, well, it's the same idea. It's just on a bigger scale. We never see anything on the size of electron positron, but hey. So, well, to me, there's some, some philosophical and some ideas that go into creation evolution ideas here, because in the end, there is really no plausible scientific explanation for how the Big Bang could have occurred. They can only talk about after the Big Bang, a certain time after, we can start talking about how things transpired, but not what caused it. And of course, if you say that something caused it, that something would be taking you back to a god, probably. And so the only other idea that you really hear posited is that of a bouncing universe, that a universe collapsed and the energy from that collapse created this universe. But that doesn't really answer anything because it just extends the problem. It moves it back further in time. What happened before to make that universe that collapsed, or the one before it? Anyway, we're out of time. Little fun philosophy to go with. Ideas that you're now going to use in your homework. So I'll see you tomorrow. Maybe. If you don't show up, I won't be heartbroken.
They'll be there.
Okay.
I'll be right across the hall.
All right.